Have you ever wondered what it would feel like to travel at the speed of light? To cover 186,282 miles in just a blink of an eye? In the realm of physics, the speed of light isn't just another number, it's a cosmic speed limit, a constant that governs the fundamental laws of the universe. Imagine being able to traverse the expanse of our solar system, from the fiery surface of the Sun to the icy rings of Saturn, in a matter of minutes. That's the power of light speed. In the vacuum of space, light moves at an astounding speed of approximately 186,282 miles per second. That's so fast that light from our sun takes just over 8 minutes to reach our planet, even though it's 93 million miles away. This speed isn't just impressive, it's the ultimate limit. According to Einstein's theory of relativity, nothing in the universe can travel faster than light. This isn't simply a rule of thumb or a guideline, it's a fundamental law of nature. It's this limit that forms the basis for much of our understanding of space, time, and the very structure of the universe. But why is this so? Why does the universe have a speed limit? The answers lie in the heart of Einstein's theories of relativity. These theories tell us that as an object moves faster, its mass increases, and it takes more energy to continue accelerating. Once we reach the speed of light, we'd need an infinite amount of energy to go any faster. Hence, light speed is the ultimate speed limit. But what happens as we approach this ultimate speed limit? As we inch closer to the speed of light, the universe begins to behave in strange and fascinating ways. But that's a story for the next scene. So, buckle up as we prepare to dive deeper into the mysteries of light speed and the very fabric of reality. As we accelerate towards the speed of light, the universe doesn't just sit idle. It responds in mind-bending ways. Now let's imagine us in our starship, throttling up, and the speedometer ticks closer to that magic figure, 300,000 kilometers per second, the speed of light. As we approach this cosmic speed limit, the universe starts to play tricks on us. Firstly, we encounter something called the aberration of light. This is a phenomenon where light appears to come from a different direction than it actually is. So if we're racing towards a star ahead, the starlight seems to shift, as if the star is more directly overhead. The faster we move, the more pronounced this shift becomes. At near light speeds, all the stars ahead would seem to crowd into a small bright disk, a bit like a cosmic bullseye. Then there's the Doppler effect, a term you might have heard in the context of sound, like the change in pitch of a passing ambulance siren, but light waves experience this too. As we near light speed, the light waves from stars ahead of us get squashed, making them bluer, a phenomenon known as blue shift. Similarly, the light from stars behind us gets stretched out, becoming redder or redshifted. So if you're looking ahead, the universe would appear bluer, and if you glance back, it would seem redder. But the universe has more tricks up its sleeve. There's something called the searchlight effect. As we speed up, light from stars that were initially outside our field of view gets bent into view. The universe ahead not only appears brighter due to blue shift, but also because more starlight is squeezed into our field of view. These are just a few of the strange phenomena we would experience as we approach light speed. But they are not just fascinating quirks. They're fundamental aspects of our universe, built into the very fabric of space and time. They remind us that the universe isn't just a stage where the drama of physics plays out. It's an active participant, responding and reshaping itself in response to our actions. And these are just the beginning. As we go faster, things get even stranger. So buckle up as we continue our journey into the realms of relativity and high-speed physics. We'll delve deeper into more mind-bending phenomena like time dilation and length contraction. So stay with us as we unravel the mysteries of the universe at light speed. Imagine if you could slow down time. Sounds like science fiction, right? But it's a real effect of traveling at high speeds. Welcome to the intriguing world of time dilation, a consequence of Einstein's theory of relativity that challenges our everyday perception of time. At the heart of time dilation lies a simple but powerful idea. The faster you move, the slower time passes for you relative to someone who is stationary. In essence, time, much like a flowing river, doesn't always run at the same speed. It can slow down, it can speed up depending on how fast you are moving or how much gravity is pulling at you. Let's say you're on a spaceship traveling close to the speed of light while your twin stays back on Earth. According to relativity, if you were to return to Earth after your high-speed journey, you'd find that your twin has aged more than you. This isn't because of some mystical twin magic, rather it's an outcome of the time dilation effect. To your twin on Earth, your clock on the spaceship was ticking slower. It's fascinating, isn't it? However, it's not just theoretical. Time dilation has been tested and confirmed in numerous experiments. One of the most famous ones involved atomic clocks, the most accurate timekeepers we have. In the 1970s, scientists placed atomic clocks on board commercial airliners. After the planes completed their flights, the clocks were slightly behind the ones that stayed on the ground. The difference was minuscule, but it was there. Just as Einstein's equations predicted. You might be wondering, why does this happen? Well, it all comes down to a fundamental postulate of special relativity. The speed of light is the same for all observers, no matter how fast they're moving. This means that if you're traveling close to the speed of light, time must slow down for you to ensure that light still travels at its constant speed. As we approach light speed, time dilation becomes increasingly pronounced. At 90% of light speed, time slows down to half the rate it would at rest. At 99.9% it slows to 100th, and if, hypothetically, you could reach the speed of light, time would stand still altogether, frozen in an eternal moment. But remember, this slowdown isn't something you'd notice if you were the one moving. From your perspective, time would seem to flow normally. It's only when comparing your clock to someone else's who's at rest that the difference becomes apparent. In this dance of space and time, the universe reveals its true elastic nature, stretching and squeezing, speeding up and slowing down. It's a reality far removed from our everyday experiences, a reality where time is not a steady, unchanging river, but a malleable stream that bends under the influence of speed and gravity. But time isn't the only thing that changes as we near light speed. As we'll see in our next segment, space itself undergoes fascinating transformations. Stay tuned as we dive deeper into the surreal world of relativity. If time can stretch, can space contract? The answer is yes, and it results in some interesting visual effects. As we move at speeds that approach the speed of light, space seems to contract in the direction of motion. This phenomenon, known as length contraction, is another mind-bending consequence of high-speed travel. According to the theory of relativity, an object moving at a significant fraction of the speed of light would appear shorter in its direction of motion, compared to its length when at rest. This isn't an illusion, but a real physical effect. From the perspective of a stationary observer, the moving object is indeed shorter. Yet this isn't the only visual oddity that occurs. As we delve deeper into the realm of relativity, we encounter a phenomenon known as the Terrell-Penrose rotation. Imagine that you're on a spaceship moving at nearly the speed of light. As you look out of your window, the world outside doesn't look quite right. Objects that should be behind you appear to be in front, and everything seems to be squished and rotated. This is the Terrell-Penrose rotation, a result of the way light from different parts of an object reaches your eyes at different times. To visualize this, consider a circular spaceship window. If you're stationary, you would see a panoramic view of the stars outside, but as you speed up, the light from the stars behind the spaceship takes longer to reach you than the light from the stars in front. This causes the stars behind you to appear rotated into your field of view. The result? A bizarre, distorted view of the universe. However, it's essential to remember that these effects are not illusions or mere tricks of the light. They are real, physical phenomena that occur due to the fundamental properties of space and time. They challenge our everyday perceptions and force us to reconsider our understanding of reality. But here's the catch. These effects wouldn't be noticeable unless you're moving at a considerable fraction of the speed of light. At everyday speeds, these distortions are so minuscule that they're impossible to detect. It's only when we venture into the realm of high-speed physics that these effects come into play. In the end, these phenomena serve to illustrate the strange and counterintuitive nature of the universe. They challenge our intuition and push the boundaries of our understanding. They make us realize that the universe is not as it seems, and that our everyday perceptions can deceive us. So we've seen that space and time can warp at high speeds, but can we ever break the light speed limit? As we move forward, we'll dive into the theoretical possibilities of exceeding light speed. So buckle up, because the journey is about to get even more exciting. Faster than light travel is a staple of science fiction, but could it ever become a reality? This question tantalizes us, as we dream of exploring distant stars and galaxies in the blink of an eye. But what does science say about this? Let's delve into the theory of traveling beyond light speed. The cosmic speed limit, as we know, is the speed of light, a whopping 299,792 kilometers per second. This is the fastest speed at which information or matter can travel, according to Einstein's theory of relativity. But what if we could bend the rules? This is where the concept of a warp drive comes in. A warp drive, as theorized by physicist Miguel Alcubierre, could potentially allow us to travel faster than light. How? Not by moving the spaceship itself, but by warping the fabric of space-time. Imagine pulling a rug towards you. The rug doesn't move across the floor. Instead, the floor itself is pulled towards you. Similarly, a warp drive would contract space in front of it and expand space behind it, creating a bubble of space-time where the spaceship would sit. This bubble could then move faster than light, taking the spaceship along with it. But creating such a warp bubble would require something called negative energy, or exotic matter, a form of matter that's predicted by the equations of general relativity but has never been observed. Producing this exotic matter, and enough of it, poses a significant challenge. We now turn to Dr. Laura Kranz, a theoretical physicist, to shed some light on this. Dr. Kranz explains, "The idea of a warp drive is fascinating and theoretically possible, but we're still far from making it a reality. The energy requirements are astronomical, and we don't yet know how to create or control exotic matter. But science is always advancing, who knows what we'll discover in the future." In essence, while the concept of faster-than-light travel is theoretically possible, it remains firmly in the realm of speculation. The hurdles to achieving it are immense, requiring breakthroughs in physics that we can't even imagine yet. However, this doesn't mean we should give up on the dream. The history of science is filled with ideas that were once considered impossible, only to later become reality. Who's to say that faster-than-light travel won't be one of them? While we're still far from achieving faster-than-light travel, it's fascinating to consider the possibilities. As we look to the stars, we can dream of a future where the vast distances of the cosmos are no longer an insurmountable barrier, but a gateway to endless exploration and discovery. The ability to travel at or beyond the speed of light would revolutionize our understanding of the universe. Ponder for a moment on the sheer magnitude of this statement. It's not just about the thrill of zipping through galaxies or the allure of exploring distant stars. It's about redefining our perception of reality, space, and time. Light-speed travel would open up a universe of possibilities, quite literally. Distances that seem insurmountable today would be within our reach. Imagine, if you will, a future where interstellar travel is as common as taking a flight from New York to Tokyo. We could explore the farthest reaches of our galaxy and perhaps even venture to neighboring galaxies. The secrets of the cosmos, once concealed by the vastness of space, would be ours to discover. But it's not just about exploration. Light-speed travel could revolutionize communication too. Today, even at the speed of light, it takes about 8 minutes for a message to travel from Earth to Mars. With light-speed travel, we could communicate across the solar system almost instantaneously, fostering a new era of interplanetary connectivity. But as much as light-speed travel promises, it also poses profound questions and ethical considerations. If we could travel faster than light, what happens to our concept of time? Could we potentially alter the course of history or create paradoxes that defy our understanding of reality? Could we inadvertently disrupt alien ecosystems or come into conflict with extraterrestrial civilizations? To address these questions, let's turn to our panel of ethicists, scientists, and philosophers. As they'll explain, the ethical considerations of light-speed travel are as expansive as the universe itself. They revolve around respect for life, preservation of ecosystems, and a deep sense of responsibility for how our actions might impact the universe. These experts will also highlight the importance of planetary protection, the principle of avoiding harmful contamination of celestial bodies. As we venture further into space, we must ensure that our explorations don't harm potential alien life or disrupt the cosmic order. The question of resource allocation is another critical point of discussion. With millions still grappling with basic needs on Earth, how do we justify investing massive resources into light-speed research and space exploration? It's a delicate balancing act between advancing human knowledge and addressing immediate human needs. In the end, the potential of light-speed travel is mind-boggling. It opens up a universe of possibilities, but also a universe of responsibility. It compels us to reconsider our place in the cosmos and our duty towards it. Such advanced technologies could change everything, but they also raise important questions. As we stand on the precipice of this new frontier, we must ensure that our pursuit of knowledge is guided by wisdom, responsibility, and a deep respect for the universe and all its inhabitants. Today, we've ventured into the realms of high-speed physics and looked at how our perception of the universe changes dramatically at high velocities. We've touched the surface of an ocean of knowledge, as vast and mysterious as the cosmos itself. We began by defining light speed, the ultimate limit according to physics, a speed so great that it takes light just over 8 minutes to travel from the sun to our planet. We've seen how, as we approach this speed, the familiar becomes strange, the ordinary becomes extraordinary. The aberration of light and Doppler shifts alter our view of the universe, transforming starlight into a dazzling spectacle. We then delved into the mind-bending concept of time dilation, where time itself slows down relative to observers at rest. We imagined a universe where leaving for a light-speed journey might mean returning to find centuries have passed on Earth. We explored the bizarre distortions of Terrell-Penrose rotation and length contraction, where objects appear visually contracted and rotated, reshaping reality as we know it at speeds close to light. We dared to ask, can we go faster than light? We discussed the theoretical concept of a warp drive, how bending space-time might allow us to circumvent the light speed limit, and how these concepts, once confined to the realm of science fiction, are now being seriously considered by physicists. We also confronted the profound implications and ethical considerations of light-speed travel. It's not just about the technology, but also about how such advancements could reshape our understanding of the universe and our place in it. While we may never personally experience these effects, it's a fascinating journey to understand the universe we live in. The mysteries of light, speed, and relativity are a testament to the human spirit, our relentless curiosity, and our undying thirst for knowledge. Join us next time as we explore black holes and the warping of space-time. It's a journey you won't want to miss as we continue unveiling the mysteries of our universe.